Greetings and welcome to session 6 on unit number 6, dimensional analysis and simulation. This session we are going to discuss the Reynolds Model Law. These model laws are based on the dominant of the forces in addition to the inertia forces. So as far as Reynolds Model Law is concerned, in flow situations where in addition to inertia force, viscous force is the other predominant force. The similarity of flow in the model and its prototype can be established if the Reynolds number is same for both the systems, that is model as well as prototype. This is known as Reynolds law, and according to this law, the Reynolds number of model is equal to the Reynolds number of prototype, where M and P are the suffix for model and prototype respectively. So where rho m is the density of the model, Vm is the velocity of the model, velocity of flow in the model, Lm is the length or linear dimension of the model, mu m is the viscosity of fluid in the model, and remaining quantities, that is rho p, Vp, Lp, and mu p, are the corresponding values of density, velocity, linear dimension, and viscosity of the fluid in prototype. So if we rearrange these particular terms, so rho p by rho m, multiply by Vp by Vm, multiply by Lp by Lm, multiply by mu m by mu p, that is equal to 1. So taking all the terms on one side, then equating 1. And if we consider this ratio as density ratio, this ratio as velocity ratio, this is length ratio, this is viscosity ratio, and all these are the suffix, all these are with suffix r, then we can have the Reynolds number for all ratio, that is equal to 1. So this is called as a Reynolds model law. Reynolds model law is mainly applicable for following fluid phenomena, where uh, that can be a sufficient criteria for similarity of flow in the model. So following are some examples where Reynolds model law is applicable, that is motion of airplanes, where there is a friction, a large friction is there, and in order to calculate the skin friction, the viscosity plays an important role. Even though inertia force is there, but because of the high velocity, viscosity force is also dominant. Second, flow of incompressible fluid in a closed pipeline. There also this Reynolds number. So wherever there are frictional forces are calculated, their Reynolds model is important. Like motion of submarine completely underwater and flow around structures and other bodies immersed completely under moving surfaces, moving fluids. So these are the applications. So especially in the application where the skin friction drag is obtained or where the frictional force is obtained, there that is because of the viscosity, there the Reynolds model is applicable. So we'll see through this particular example, we'll see how this Reynolds model is applied for solving numerical. Now, in this case, the resistance R to the motion of a completely submerged body is given by a relation. So in the dimensional analysis, in Buckingham pi theorem, we have derived this. So Reynolds number, resistance is a function of this parameter as well as Reynolds number as well. So where rho and V, nu are the density, this is nu, are the density and kinematic viscosity of the fluid, while L is the length of the body and V is the velocity of the fluid. If the resistance of 1/8 scale airship model, so the airship scale model is given, that is maybe a geometrical similar model is given. So the model is 1/8 scale as that of a prototype. When tested, so when the model is tested in water at 12 meter per second, and its resistance is coming, that is 220 Newton. What will be the resistance in the air of the airship at the corresponding speed? Kinematic viscosity of air is 13 times that of water, and the density of water is 810 times that of air. So while solving problem on model analysis or similarity, uh, from the given data or from the given statement, we have to write the data in appropriate unit. So if that data is applicable to model, we can write with suffix n. If that data is applicable to prototype, we use the suffix p. So as per the given information, generally in model testing now in this situation, the airship model is tested in water and where the velocity of the model is maintained at 12 meter per second. And for that velocity, the resistance come around 220 Newton. So the model is developed that is scaled down up to 8 scale, that is 1/8 scale. So from this statement, we can write the given quantities. So this is a situation in actual prototype where this particular aircraft, it offers or the air, because it generally moves at a very high speed. So there is a large resistance here offered to this airplane by the air. So we have to calculate in actual practice what should be the value of this resistance. So given quantities, the scale ratio is given. Scale ratio is generally the length ratio, that is always based on this particular value, as the model of ship is always smaller than that of prototypes. So always this 1/8 means LM, if it is 1, LP is 1/8. So LM by LP, this ratio is given. Velocity of model is given 12 meter per second. Resistance of the model is given, Rm is 220 Newton. The fluid for model and prototype are different. So for model, it is water. For prototype, it is air. Kinematic viscosity of air, that is model, is given. Sorry, that is for prototype. That is 13 times the kinematic viscosity of water. And density of water, that is 810 times that of density of air. Now, obviously, in this particular case, the viscosity is given, so we can use, and in the relation also, in the Reynolds number is a dominant number. So without any doubt, we can use the Reynolds model here in order to calculate the required required parameter, that is resistance. So according to Reynolds model, we have either rho Vd by mu, rho Vl by mu, or as the kinematic viscosity is given, so Vl by nu of model, that is equal to Vl by nu for prototype. Now in this case, Vm is given, Lm, Lp is given, Vp is still unknown. That Vm, that kinematic viscosity ratio is also given. So putting these values, because only unknown in this equation is Vp, we can calculate Vp. So that is a velocity of actual prototype, that is 19.5 meter per second. Now, at this prototype velocity, the resistance we have to calculate. So already the relation is given. So for this relation, we can use this relation for model as well as prototype. So for this relation, one more dimensionless term is there, that is R upon rho L square V square. So we can use this relation for prototype. So that is R upon rho L square V square for model, that is equal to R upon rho L square V square for prototype. Because we have to calculate this resistance. So in this case, in addition to the Reynolds model, because Reynolds model help us to determine the remaining property of or remaining parameter of the prototype. Velocity we already calculated. In order to calculate the resistance, the different correlation is given. So R upon rho L square V square, that is equal to VL by nu. So this similarly, if the Reynolds model is valid for the model and prototype, the resistance model is also valid for model and prototype. Now we can write in this case, the resistance of model is given, density of both are there given, the ratio is given, means both density is known to us. Length ratio is also known to us, velocity ratio also known to us. Only unknown is the resistance of prototype. Yes. If you rearrange the term and putting the values, because here directly the densities are not given, but the density ratio, suppose rho air, rho air, so rho water to rho air, that is 810, and kinematic viscosity of air, that is nu A to nu water, that is 13. So if we're rearranging the equations and put these ratios in this above equation, only unknown in this equation is the resistance experienced by the airship, actual prototype. So from this we can calculate the RP value that comes around 45.9 Newton. So this way we can predict the performance of actual system, because the model is very small. So this is the beauty of this model analysis. It saves our time as well as costing. So because actual prototype testing is quite expensive and time consuming also. So if you perform the test on uh, the model, and then based on the model analysis, we can predict the performance of the actual prototype using the different model laws. So in this case, we have used Reynolds Model Law. And accordingly, once we know this resistance, then we can calculate what is the power required to overcome this particular resistance. So accordingly, the engine capacity will be developed and other things. So if you have to minimize this particular resistance, the other corrective measures are taken. So this is very important concept, as well as for large systems, large machines, or large infrastructure is there. So there, this model analysis is very much useful. We already discussed in model analysis and simulated section. So that's it from this particular session. At the end of this particular session, you could be able to explain what is a Reynolds Model Law with its application. And you will be also able to apply this Reynolds Model Law to solve engineering problems. But the crux of solving problem is to identification of suitable model law, because now this is we are discussing this model law separately. So it is not easy. It is not difficult to recognize. Yes, as this chapter is going on, that is Reynolds Model Law. Whatever may be the numerical that is applicable for Reynolds Model Law. But in actual practice, you should be able to recognize which particular model is applicable, and that easily we can recognize with the help of statement. If you solve n number of problems, then you can easily recognize. So, and based on the dominant forces, in addition to the inertia force, we can easily recognize. That's it from this particular session. Thank you very much.